Here we're going to look at the role of symmetry in problem solving, and we're going to look at a couple of different types of symmetry. First, geometric symmetry, which is something that you probably are familiar with, and then second, algebraic symmetry, which is also something probably you're familiar with, but maybe you've never thought of it that way before. But before we do that, let's look at a very rough definition of what it means to be symmetric. So an object is said to be symmetric if it remains unchanged after something acts on it. And now what could this action be? Well, it could be almost anything. And I've built up some examples so that we could see that. So maybe a first example would be this geometric symmetry. So let's say we've got this square right here. So these vertices A, B, C, and D are not parts of the square. They're just there for labels so we can see what's going on. So there are 8 symmetries to this square. You can do all sorts of rotations and you can do reflections about 4 different axes. So I've written the rotation with this purple like circle, so that means like 90-degree rotation. And then we could also take a reflection through that green dotted line. Now notice if we rotate by 90 degrees through the center, the vertices get permuted in the following way. So this A, which is in the top left, will go down here to the bottom left, and then so on and so forth. But other than the fact that the vertices are permuted, if we deleted the names of the vertices, this would be an object that was unchanged. In other words, we wouldn't be able to tell the difference between the original and the final version. Similarly, if we reflect this thing through the axis, which is green, we wouldn't be able to notice the difference between the original version and the final version without the labels on the vertices. Okay, now here's another little example. And so here we've got this infinite sequence of A's and B's. And so the sequence goes like this: A, B, B, A, B, B, A, B, B, A, and so on and so forth. So notice this has some symmetry to it as well. And the symmetry that we have is that we can translate this thing 3 units, and by 3 units I mean 3 letters, and the sequence remains unchanged. Now notice this only works if it's an infinite sequence in 2 directions. Otherwise, you would like bump up against the end or the beginning of it. And notice this translation can happen to the right or to the left. So if we're doing the translation from this original sequence to the new sequence, notice this underlined A becomes this new underlined A. And then maybe this underlined B becomes this new underlined B, and then so on and so forth. Notice this underlined A comes from something that is part of this like ... which is telling you to take the same sequence in the left. Okay, good. So there are 2 different types of geometric symmetry. Obviously, there are a bunch of more types, but you can think about some more on your own after looking at these types. Now I want to talk a little bit about algebraic symmetry. So first, I want to look at this polynomial. We'll call it f of x, y, z. So it's a polynomial with 3 variables, and it's equal to 3xyz plus x squared plus y squared plus z squared. And notice this polynomial is symmetric about any permutation of x, y, and z. In other words, we can switch x with y, and this thing does not change. We can switch x with y, y with z, and then z back with x, and doesn't change. Any kind of permutation that you do of x, y, and z, this polynomial will not change. This actually has a name to it. It's called a symmetric polynomial. Okay, good. And then next, if we look at this inequality, so it's a plus b times a plus c times b plus c is less than or equal to 8abc. So this inequality is symmetric about any permutation of a, b, and c. And so that actually gives us a hint for how we would show that this inequality was true. And maybe we could prove this inequality by looking at a smaller version of it and then apply symmetry to the smaller version of it 3 times. And what would the smaller version of this inequality be? Well, it's exactly this inequality. A plus b is less than or equal to 2 times the square root of ab. And that is exactly the arithmetic geometric mean inequality. So I'll actually leave it to you guys as a little exercise to show how this arithmetic geometric mean inequality will imply this inequality involving A, B, and C. Okay, let's go ahead and clean up this board, and then we're going to launch into a couple of examples. So our first example will have to do with some geometric symmetry. So we've got this following setup. So we've got a square with side length 1, and then inside that square we have a circle which has been inscribed. And inside of that circle we have a square which has been inscribed. So we've got an outer square, a middle circle, and then an inner square, and this inscription is going kind of inside. Okay, and now our question is, what is the area of the inner square? So there's a solution to this that will not use symmetry, that will involve the Pythagorean theorem and just some algebraic manipulation. I'll leave it to you guys to find that solution if you want to. I want to use a solution that involves symmetry. So here's my solution. So if we look at this, what can we do so that we can put some more symmetry into this picture? So I think maybe the best bet is to rotate this inner square. And so this vertex of the inner square is inside the line segment, which is one of the sides of the outer square. So let's maybe write it like this. So we're going to rotate the inner square so that we have the following picture. So there's our outer square. Now we have our circle, which is inscribed. Good. And now we have rotated our inner square so that it looks like this. Great. And now that we've done that rotation, can we exploit the symmetry to easily see what the area of this inner square is? So let's look at it for a little bit. Maybe as is, it's not clear what to do, but if we add 2 more line segments, it will be clear. So let's add a line segment from here to here. So that's one of the diagonals of the square. And then another line segment from here to here. So that's another line segment of the square. And notice this is going to break up the bigger square into 8 congruent triangles. So let's maybe write that down. So the big square is broken into 8 congruent triangles. And so what are those triangles? Well, maybe I'll bold some of them. So here's one of the triangles right here. So that would be one of the triangles, for instance. And then another one would be like this triangle right here. But then there are 8 in total. So there's 1, 2, 3, 4, 5, 6, 7, 8. Great. So now also the inner square is broken into 4 of these triangles. These triangles. But we know the area of the outer square is 1 because this thing has side length 1. 1 times 1 is 1. But now by the way that we've broken these squares up, we can see that the area of the inner square is 1/2 the area of the outer square. But that tells us that the area of the inner square is equal to 1/2 because the area of the outer square is 1. Okay, so that's good for this problem. So let's go ahead and clean up this board and we'll look at another one. Now we're going to look at another problem where we can exploit geometric symmetry. So our goal is to find a real number a such that the region bound by y equals ax plus 3 and y equals x squared minus 3, that should be a squared, is minimum. Okay, so I've drawn a little picture of what's going on here. So I've got my x-axis, I've got my y-axis. Down here I've got my point 0, minus 3. So that's the vertex of this parabola. Up here I've got this point 0, 3. So that's the y-intercept of this line. I've called the y-intercept of this line O because this is like kind of going to be the origin for our setup geometrically of this whole picture. I know the origin is down here, but I'm going to call this O because you see it'll play like a central role. Okay, and what we want to do is tilt this green line in a way that makes this area right here as small as possible. So you could most definitely use calculus to do this. And so you could find this area as a function of a using a definite integral, and then use the extreme value theorem in order to calculate the maximum value. Or sorry, I should say the minimum value, but we're going to do it strictly geometrically. Okay, so the first thing that I want to do is draw a horizontal line through this point 0, 3. So I've got this horizontal line that goes like this. Great. And now what I want to do is name some points. So I'm going to name this point over here A, so that's going to be the intersection of the horizontal line y = 3 and the parabola. I'll name this point over here B. So the next thing that I want to do is name the intersection points of the green line and then the orange parabola. So I'm going to name this one C, and I'll name this one up here D. And next I want to introduce 2 more points. And those points will be achieved by dropping a perpendicular from this horizontal line until it hits the green line. And then similarly here, we'll draw a perpendicular up from that horizontal line, well, the same horizontal line until it hits the green line. Notice that that is the same thing as making a line which is parallel to this y-axis, and then we know that parallel lines are unique. Okay, so here, let's do that. So I've got something like that. So that goes straight down to this point right here. I'll go ahead and call that E. And then something like this. So this is going to go straight up. So I'm going to call that F. Good. And now the next thing that I want to notice is that I've got 2 triangles built into this picture, which are most definitely congruent. So let's notice that triangle OAE is congruent, so I'll write it like that, to triangle OBF. And that's because one of these is the image of the other by a reflection through this point O. So let's maybe write that down. So they are reflections through the point O. Great. Now the next thing that I want to do is notice that I've got 2 more triangles which are interesting. This one which is OAC, so that would be like that. And then this other one which is OBD, like that. And one of these triangles is smaller than the triangle OAE. In other words, this triangle over here on the left. And the other one is larger than OBF. And those 2 are congruent. So let's see what that tells us about some areas. So let's notice we have the area of triangle OAE is equal to the area of triangle OBF. So why is that? Well, that's because they're congruent to each other. But then let's also notice that the area of triangle OAE is going to be bigger than the triangle of AOC. So area triangle AOC. And then the area of triangle OBF itself is going to be smaller than the area of the triangle OBD. So let's see, we've got area triangle OBD. So now let's look at the extreme left and right hand part of this inequality. So we've got this triangle AOC is less than the triangle OBD in area. But what does that tell us? Well, that tells us that as we tilt this line, we end up adding more area above than we are subtracting below. So the area of the portion added above the line y = 3, so notice that's our blue line, is always bigger than the area added below the line y = 3. So if we're always adding more area above than we are subtracting below, then that means tilting this line is always going to give us a larger area than if we just had a horizontal line. But what that tells us is that the minimal area is achieved by a horizontal line, but a horizontal line has slope of 0. In other words, A is equal to 0. So let's write that down. So minimal area achieved by A equals 0. Okay, good. So now let's go ahead and clean this up, and then we're going to look at an example or two of algebraic symmetry. So we just used geometric symmetry to solve a couple of problems that would have been extremely messy if we had used analytical methods. So here we want to use algebraic symmetry in order to simply solve some algebraic problems. So the first thing that we want to do is find the roots of this quartic polynomial. In other words, we want to solve the equation x to the fourth plus x to the cube plus x squared plus x plus 1 equals 0. Now this is completely possible using the notion of complex roots of unity, but we're going to do it a different way, just using symmetry. So the first thing that I want to do is maybe divide this by x squared in order to symmetrize this equation. So let's maybe write that down. So symmetrize by dividing by x squared. In other words, multiplying by 1 over x squared. Notice that x equals 0 is not a solution to this equation, so we're not deleting any solutions by doing this. Okay, so let's see what that gives us. That's going to give us x squared plus x plus 1 over x plus 1 over x squared equals 0. Now there's some nice symmetry to this equation. We can like fold this equation right here, and in some ways the left hand and the right hand side are symmetric to each other. Okay, now the next thing that we want to do is make a change of variables involving this symmetric structure. So the change of variables that I want to make is y equals x plus 1 over x, because that is kind of at the heart of all of the symmetric structure of this. But now notice if y equals x plus 1 over x, well, we're going to need an x squared and a 1 over x squared term. So that means we're going to need a y squared term. And y squared will be equal to x squared plus 2 plus 1 over x squared. So that's what you get by foiling that out. That's because x times 1 over x is 1. Great. But now we can substitute this value of y and this value of y squared into this equation, which was a new version of our goal equation, to get the following. So notice we'll have y squared plus y. But notice y squared plus y is everything that we have in this equation, but plus 2 instead of a plus 1. So we can make it exactly what we need by subtracting 1, and now we have that equals 0. So now we've got the equation y squared plus y minus 1 equals 0. That's a quadratic equation, shouldn't be too bad to solve. So let's do that. So we have y equals, so we can't really factor this very easily, so maybe we'll use the quadratic formula. So negative b, that'll be minus 1 plus minus the square root of b squared minus 4ac, so that's going to be the square root of 5 over 2. So notice that has something to do with the golden ratio, which is nice. Okay, good. So now what we want to do is plug this value of y up into our original substitution, and now we can solve that for x. So let's go ahead and do that. So that's going to actually give us two equations to solve. Maybe we'll do one of them here and then talk about what we get for the other one maybe at the end. Okay, so let's do the one with the plus first. So notice we'll have minus 1 plus the square root of 5 over 2 equals x plus 1 over x. So as it is, that would be hard to solve, but maybe what we can do is rewrite it as a quadratic equation. And then maybe while we're at it, we can rewrite this thing as phi, because that's a common name for the golden ratio. And notice that we can multiply both sides of this equation by x, and we get phi times x equals x squared plus 1, which is the same thing as x squared minus phi times x plus 1 equals 0. Now we've got a quadratic equation that we can solve with the quadratic formula. So that's going to give us x equals negative b, so that's going to be phi, plus minus the square root of b squared minus 4 times a times c, so that's going to be phi squared times 4 times a times c, or sorry, minus 4 times a times c, so that's going to be minus 4 all over 2. So now I'll leave it to you guys to simplify this. It's really more of a bookkeeping exercise and careful arithmetic, but I will say that you get the following. So we're going to have negative 1 plus the square root of 5 plus or minus I times the square root of 10 plus 2 times the square root of 5 all over 4. Great. So that's what you get for the solutions attached to this plus. Now you might ask, well, what do we get for the solutions attached to a minus? Well, that's just going to give us a plus or a minus here and a plus or a minus here, giving us 4 total solutions because we've got a choice of a plus minus here and a choice of a plus minus here. And that's going to be all 4 solutions to this quartic polynomial. Okay, I'm going to go ahead and clean this up. We're going to look at one more example. So we're going to do one more example. We're going to solve the following system of equations. So we've got x plus 2y plus 3z equals 30, 2x plus 3y plus z equals 30, and 3x plus y plus 2z equals 30. And so just like essentially all of the other ones that we've done in this video, you could do this in a straightforward computational way, but it's going to take a lot longer than if we exploit symmetry. And the symmetry that I want to exploit here is to notice that if we have a solution, x, y, z, that solution must be invariant as we permute x, y, and z. And that's because notice that if we permute x, y, and z in this equation, we're going to grab one of these other 2 equations. Okay, so let's maybe write that over here. So any solution will be invariant under permutations of x, y, and z. So that tells us that our triple, which is a solution, has to have all 3 the same parts. In other words, x equals y equals z. But now that we've achieved this equation, x equals y equals z, we're pretty much home free. We can plug this into any of these 3, and we'll see immediately that 6x equals 30. But then that tells us that x equals 5, but that also tells us that y equals 5 and z equals 5. So we've quickly come to a solution. Okay, great. That's a good place to stop.